All right, well, welcome to our March 2nd, 2019 Structural Modeling Video Conference. Today we're going to cover a lot of ground. It's kind of an integrative type of session today. It's going to cover work we've been doing about the last 2 years. We're going to step back to some work that Mary and I did about 10 or 15 years ago, and also way back to the work that Brian Marr did at the University of Washington 30 years ago. And try to tie these together, and talk about our pathway forward. So, in this particular session on basic system concepts, the goal is to talk about the limitation of human memory and how this limitation becomes a constraint in in the process of groups working together when they really don't have much information about the situation at hand. They need to talk with each other, they need to exchange information, they need to come up with new ideas. So basically, the capability of the human beings to make these decisions and understand this information is limited by their short-term memory. The, the, that specific triadic law of mind compatibility was identified and documented by Warfield. We've talked about that in the paper. Also, we talk about this idea of a concept cube. The concept cube essentially takes the three dimensions, and provides us a framework and a way to start thinking about and looking for possible relationships between things, between ideas and concepts. So Mary and I came up with this idea a few years ago. We've kind of kept it in the background. One thing that we have done is that fits with the general concept cube is, of course, the logic cube, which we've worked on a lot recently. And then that specific components in the concept cube, we specialized into the logic cube, the asset cube, and of course the PMO cube, which was a variation on the work that Marr did at the University of Washington, which we will talk about a little more later on. So the outcome of our work with the logic cube and looking at that specific part is that it looks like that categorization, making categories, grouping things, clustering things, and ordering things, putting things in order, are the two things that human beings are really good at doing logically within groups. They can make those types of decisions. If they have the information, then they're fairly good at doing that. When we get into intervals and ratios with human beings, they're not that good at that. They need scientific equipment, they need measurement scales, they need a lot of things to support their view of the world when they go into interval and ratio. So in the measurement scales and in categorization and order, we're doing well with unaided human interaction. One of the things as we step back and look at the work that we did a few years ago is when we were looking at evolutionary programming and clustering systems and configurations. We were looking at the work of Derek Hitchens and others who worked in the area of automated n-squared charts. But when you put an evolutionary algorithm and let it work on a group of objects in the system to cluster them, and you interpreted that specific outcome, then you were also working with clusters and order, because the evolutionary algorithm would order that piece. So that's generally what we're going to cover today, and try to make that big overall connection and work forward from there. So let's go into the paper. Here. Okay. So basic system concepts. Again, we've taken a look at a variety of definitions and looked at these over a period of time. And we selected the primary attributes of any system as being structure, behavior, and context. At a very high level, we believe that these are facets of a system that are universally addressed in some way. And in this specific instance of dealing with the concept, we said these primary attributes are then further evaluated as secondary attributes, which are abstract, composite, and physical, where composite is an aggregation of abstract and physical. So, as I said, we're going to go through and look at the general system cube. We're going to look at the concept cube that Mary and I developed, and we've now put that into general system cube, and the logic cube, and then some of the other things that we've developed in the past. And the new part here is the one where we have now applied it to the modification of Marr and Marius's FRAT approach, which we now have cast as PMO within 3 parts of that. And I believe that is probably the most straightforward way, or the simplest level to start getting a handle on these specific concepts. And we'll talk about that a little more as we go forward. So, this is the lattice of 3 elements and subsets in the law of triadic compatibility that was put together by Warfield. It was based on the magic number 7. And what that is essentially a Miller index that says human beings can keep 7 plus or minus 2 things in their mind at any one period of time. And if you're in a new situation and you really don't have any rule sets and you have to think about everything, then the most you can have is 3 elements to keep to evaluate in any detail, because the permutations in this lattice of 3 elements is 8, but the empty set, you take the empty set out, then you only have 7. So that's essentially the limit of dealing with 3 elements. And just as an aside, if we define the system as a relationship mapped over a set of objects, then if one of these elements is a relationship and the other 2 are objects, then we kind of have a corollary, another corollary to the law of triadic compatibility, and that's the principle of a single system relationship. Because if you have more than one, then you overload the human being. So, and that was a design criteria and a design process in the art, where we took the single relationship for each plane, but we had multiple planes and multiple dimensions, and then you can use other functions to integrate those specific representations. So this is the statement of the law of triadic compatibility. The human mind is capable with the demand to explore interactions among a set of 3 elements. And so that's a criteria, I believe, that is missed all the time. It's a design constraint. And in many cases, we overload the human beings that we need the support from, and then that sets everyone up to fail. And of course, then there's the principle of division by 3s from Warfield, which is a corollary to the law of triadic compatibility, which introduces division of a concept as a means of analysis is mind compatible if each division produces at most 3 components, thereby creating a tree with 1 element at the top and at most 3 elements at the second level, at the most 9 elements at the third level, and so on. So you can probably imagine this is where the idea of the concept cube came from, where we basically put together the idea of using a cube and mapping to this geometry so that we now start having a visual representation of this human constraint. In this particular part, you see the highest level of abstraction. This cube at the top has 3 sub-concepts to it. And then the second abstraction layer down, again, has each of the sub-concepts have further defined into 3 more sub-concepts, and so on. And we didn't go into the indexing here in any detail, but let's say, for example, like the logic cube, which has only 1 level of abstraction. Well, it's got, it has the 3 faces, and those 3 faces then are subdivided. So the indexing on that particular cube would just be 3 numerals, because you only have 1 cube or 27 subcubes to index. So if you have another type of concept that's represented, but that has 2 layers or has subcubes in it, like with the asset cube, then you would have 5 numerals in that particular indexing, and so on. So if you came up with a cube that only has 3 numerals in it, you would know that it's just 1 cube. But if you came up with a cube that had 5, then you know, oh, okay, I need to determine what the other associated cubes are. So there's a mechanism in indexing that's computer supported that goes along with the visuals that we don't talk about here. Okay. So we're thinking about the ideas of really from the workshop, system science workshop, where Peter was talking about, systems literacy. We're thinking, well, what are the components of systems, and what would you really need to know to be literate about a system? So we picked these 3 definitions, which are widely variant, and mapped them to the concept cube, and then integrated them. So there's an idea that the idea of jointly separable, which I first ran into when I was talking with William Combs, who did the Combs method of fuzzy logic work. But the idea is that you can integrate all of these aspects together, and they reinforce each other. So the idea of a system structure, system behavior, and system concept, you can design, system context, you can define a system using structure or behavior or context. But if you use all 3, you have a better, more robust, more functional, adaptable type of definition than if you just use 1. And so the ability to integrate these and use them is more valuable than just using 1. But using 1 is also valuable if that's all you have. If that's all the information you have, then you can use that, that's useful. So the idea is there's a graded range of these definitions. Some are more useful than others. Of course, the structure definition came from Warfield's work. Behavior is basically use Len Tronquel's work as an example there, and the context as a work of Brian Marr, which was, he worked mostly in large-scale industrialized systems, and that essentially you would take a system as defined as being part of, anything. You just need to separate it from its context and then continue that process. So these are the areas we selected to work on. The secondary concepts we picked from the area of ontology, so that we would have an abstract component and then a physical component and then a composite component. One of the reasons that support this type of selection is the idea of, let's say, you're going to build a, well, I'll say an evaporation chamber, right? Something that's physical and that works on the laws of physics. When you start thinking about that and designing it, you're in the abstract space, using the laws of physics, you're using all of the information that's been encoded in abstract form. But as you move forward and start building components, and designing components, or building test articles, things like that, then you're going to the composite realm where you say, oh, okay, I have this set of abstract properties, and I am now matching these abstract properties against the components that I've created in the physical space. And then in the physical space, you just have the tested type of article that's working. And so that, to me, is kind of helps to represent the stages that any type of design process would go through. So at that level, we picked these for the second level. And we can see now that we have the general system cube, which is structure, behavior, and context. And we have these components that go with them. And then that maps into 27 subcubes, which we've detailed below. And of course, as we talk about here, we have abstract structure, abstract behavior, and abstract context. That would be like a system of theoretical computer science sorting algorithms. Not all algorithms, it's sorting algorithms, but it's all abstract, and it's an abstract behavior and an abstract context. But if we had something that was a physical structure, a physical behavior, a physical context, we said like a wood-burning stove. You could talk about it or communicate about it in abstract terms, but the stove itself is just this physical configuration that's doing its process of oxidizing wood or whatever you're burning. And in the middle group, we have a composite structure, a physical behavior, and composite context. That would be like a chess game, where you have physical pieces, but the rules of the game are abstract. So those are the ideas and the categories that we would use to start mapping the topology of how a system would go from a very abstract concept to being physically instantiated and operating in physical space. And this helps us to start mapping specific transforms and transition spaces that a developmental system component would have to go through. So then the concept cube, of course, constructs may be used to inform the conceptual evaluation of any step associated with the general systems cube evaluation. So if you were making decisions about transitions within the general systems cube, then you could use the elements that are associated with the logic cube to do that. Just mention this here. We're not going to go into that in any detail now, but that's something later on that we believe that would be advantageous. Okay, so the general systems cube, essentially, and the concept cube examples. So kind of gone through this. It's the general system cube is just composed of a collection of the concept components, and it's used to organize and identify this structure at a very high level, but it's used to support human semantic, to support the human semantic domains that kind of limits things. So it says we're going to generally talk about things with this pattern. And one of the sentences that stuck in my mind when I was listening to one of the conversations at the System Science Working Group was a long list of things we put up on the board, and one of the participants said, well, there's no relationship between these items. And you just have this very, very long list of elements, but there's no relationship. So once you start looking at a three-dimensional cube and you start looking at these fundamental concepts, then the idea of space, the idea of interfaces, the idea of subcubes then starts mapping out where these relationships would be, so you can consider those, you can enumerate them. There may be an interface that's important, it may not be, but what it does is it starts providing a framework which you can start addressing these things. So so all of these components help establish conceptual mechanisms that can be focused on any specific development context. And so we're going to look at some of those, how we've taken the general system cube and applied it. And one of the ones that we've been working on for a while is the logic cube. The logic cube has 27 subcomponents, and it's a one-level cube. So the indexing on this cube would be 1, 1, 1, or just have 3 numerals within that. And we work with the reflectivity, the symmetry, and the transitivity, and these are used to support operations on natural language relationships and to move a natural language relationship more toward the formal space of structured graphics and mathematical representation. Okay. The way that we've outlined this and the way that we've organized this is compatible with what's going on in the cognitive structures for conceptual spaces and some of logic theories and the conceptual graph. So there's formal concept analysis and there's conceptual graphs that are well-developed theories in artificial intelligence. And these structures, like the concept cube and the different levels of the concept cube, map to many of these fundamental processes in these other areas. So again, we're not going to get into that here, but that's the idea that there's many of these connections between these different spaces. We did this a year or so ago where we talked about the logic theories, and where we made the cutoff line here at 3, the strict order and equivalence. And equivalence is the grouping, and the clustering, and strict order is the ordering. And what we have here, the difference between the abstract mathematics and within our structural modeling is we can actually ask the question, right? We don't need to have a selection rule, or if A is equal to or less than, or if B is greater than or equal to. We don't need to have that rule that supports asymmetry, because we just ask. We can get the empirical information we need at that time. And so we can have very effective engagements without having those logical rules, which introduce a lot of uncertainty and add a lot of complexity to the calculation. So basically, we cut those off at 3, and the equivalence in the strict order again match the human being with the measurement scales, remember, with nominalism and the ordinal, and also matches the benefits that we get from the evolutionary programming with the clustering and the ordering. So there's kind of an area that's developing and reinforcing these concepts as we go forward. All right, so the logical axioms support structure modeling complexity reduction. That's what I talked about a little bit. Support AI-based evaluations and techniques. And that's something that that provides the opportunity now to start provide a framework to start hooking into these other disciplines and these other tools that are available. And this, of course, is the logic cube, and this is the, you can see here the index that I was talking about, like whoops, the 111 up in the top left-hand corner, or the 333 down in the bottom left-hand or right-hand corner. So that, you see something like that, that tells you this is this structure that we're talking about, this system is a single cube. If we, up in the top left-hand corner, if you had a index up there that was 5 numerals, then you would know, oh, okay, this is this has another set, there's at least 2 levels. If it had 7 numerals, then it would be 3 levels, so forth like that. We'll go into the indexing schemes and so forth later on when we get to that point in the software. But that's the idea. That's how you know what is the scope of the concept that you're working with, is the indexing. And so the logic table is just the fundamental systems pattern, and we'll see that, establish that pattern, and now you can see that it scopes the relationships over a domain. And that can be used to address many areas. So this one, now the asset cube, is 2 layers deep. And we did this for a conference back in the middle 2000s, I guess. But the idea was that you have an asset that needs to be protected. So that sets the general context. And so the 3 things that we pulled out of there was the system, the threat, and the target. So the system is what needs to be protected. The threat is what's threatening the system. And then the target is the specific components. That is broken down into the threat cube, the target cube. In this specific case, the part of the system that's being specifically addressed is information, and this is information assurance. And then the system cube, in this particular case, is addressed as the type of system, whether it's a product system or process system or environment, specification, whether this particular component and program. So this is more of like an industrial-based system. Okay. So this just details those specific interfaces and those components. Primary thing to take away here, this is second level cube. It would be indexed differently, and you can have more levels. But the structure of the cube and the decomposition provides a standard way for the humans to guide their way through it, and then to find a place where they can reason, and their reasoning is constrained to the cube that they're in at that time. They can step up a level of abstraction and do other reasoning, but it starts now to make a reasoning system that is designed not to overload the human participants. So the FRAD approach was put together by Marin Moraes. Is again another example of a cube, but what happened here was, in the original work that Brian put together was FRA. And that was functions, requirements, and architectures. I know because I read his original documents and so forth that he basically turned into Boeing in the Boeing library. So later on, they added tests, and the tests are really part of your production system. Your production system, you do tests to make sure that your system that you built fits the case. So, and in working with the FRAT process over a period of years, we find that there was some definite overloading in terms and concepts. So we decided to take those concepts from Mar and Marias and break them into performance metrics and objects. One of the primary things about this cube is that there's a lot of work that was done by Mar and Marias that where you just use the three levels. You don't even break down into the three interfaces. And so you can start at a very high level of abstraction and decide what you need to do to create or identify a system, and then drill down from there. So the performance metrics and objects cube, put in that format, would fit, I think, very well with the unified program planning approach by Warfield or many other people, but it's very high level. It's only one level to start. You can start at the top level. You don't even need to break down into the subcubes if you don't want to start using these ideas. So this is kind of an entry level, very high level abstraction. You start using that and then start drilling down into the more detailed approaches. But at each level where it gets more detailed, it's kind of a recursive application of the other one. Okay, so Mary and I developed the abstract relation type to categorize and put this type of information together and put into a pattern, so that, as you can probably tell, we're bringing a lot of things together here in this particular paper, and we're going to use these ideas that we talked about to start looking at and discussing the idea of order. So this is an order that comes out of the, specifically out of the software that we built to emulate the GMU ISM software. And from our work here, we find that this works. This is a good approach, but using the mathematics that Warfield did at that time. But our new software will just use a binary search approach, because these are placing them in order, go from an unordered list to an ordered list. And so we will then establish an ordered list and use a binary search on that ordered list component until they're all ordered. So that seems to work better computationally. And of course, clusters of equivalent objects, again, is something that we've worked on before. This clustering algorithm that will be in the new software will be just like the clustering used in the GMU ISM software emulation. So these are things that, again, work on clusters, equivalence, and order. And this is the logic-based piece. But there's also the evolutionary genetic algorithm piece, which essentially, once you have any specific configuration, you can run a genetic algorithm to create clusters, but it also reorders the system. So again, what we have here is there's a connection between the ordering and the clustering, but from two completely different standpoints. From the logic standpoint, we've designed a system where people can that's mind compatible and people can understand it and reason about it. When you're working with genetic algorithms, you're working with very large scale systems that no one can understand. So you're putting your computer algorithms to work, and then have those computer algorithms present you patterns that then you can analyze. And I believe this is a tremendous advantage, because one of the problems with genetic algorithms is a kind of black box. No one really trusts what's going on in there. And we can now, there's some indication that we will be able to do some verification and some explaining of what's going on in these cases. And but we could do that using the ART format, right? Abstract relation type. Because the abstract relation and its representation would be essentially the same in each case. And so then, yeah, so this basically is from the work of Derek Hitchens, and then this is dependency structure matrix work. In both cases, I was not able to reproduce. No, in both cases, I was not able to implement the mathematics they presented in software. So I used a different type of algorithm in my software, but my algorithm produced the same results. So Derek and the DSM people, they use completely different algorithms than what we use, but we were still able with our algorithm to achieve the same output. So there's different ways you can do this. I also believe that our algorithm is much more efficient than either one of these two. I think the DSM clustering component that I saw was very inefficient. Derek's was better because he used more of a entropy approach, which is more well understood. And then our approach, what we do is we don't work with single cells. So the DSM approach just works with single cells and operates on that. Kind of the same way with Derek's, but in our case, we do our genetic algorithms at the system level. So we have at the minimum 2. And so we have to have at least 2 objects related to each other to be a system. And then we start our operations, and our genetic algorithms are done at the system level, not at the element level. So they're much more efficient. Okay. So obviously when an example ART construct in this particular case for clustering, we have the pros, which have clustering grouping all objects that have similar properties, right? That is the that is our logic approach. And so we have a structured graphic. One example here, figure 10. And the mathematics then is at this GitHub repository. And then cluster. Now when the clustering here, it's the metric is a dimension measure aggregated across all the objects. So a human being simply can't do that in their head. So it has to be calculated. And what you're talking about here, you're creating a cluster based on an aggregate feature of the complete system. Well, here you're creating a cluster by evaluating the properties of objects and comparing them to each other, and then creating a structure. So this clustering is impossible for a human to do, but they're compatible. The outcomes are compatible in order and clustering, and humans can evaluate the outcome. And then this bit bucket here in this clustering source component is did this software about 12 years ago. I went and chucked it. It's still, I had to change it because they changed the underlying language, Python, in the interim, but it works. And so the idea is to actually run a genetic algorithm to create clusters. Okay, so we're working okay. We're right on time. And right along. So summary and conclusions. So obviously we presented an array of basic system concepts, and they range from general to specifics. And again, primary part of this work is based on Warfield laid the foundation for the development of the general and genetic systems concepts, the generic system concept. And the concept cube, of course, is based on the law of triadic compatibility. And the effective complexity engagement is the primary goal. So what we've done now is said, okay, if you put these logic components together, humans can engage them. But there's obviously system configurations that are so complex, humans can't engage them. And so when we apply things, artificial intelligence algorithms like computational search and evolutionary programming, then the outcomes of both of those specific activities can be matched. And so the humans can compare those. So that kind of gives a window into the black box AI world that lets people have more confidence in exactly what's going on within that computer process. And the evolutionary programming doesn't really have to give you just one answer, right? It can give you a range of answers. And you can compute them again and again, so that computing power is so cheap now that you can run this stuff in the background, looking, searching all the time, looking for these specific patterns. But the challenge, of course, then is what patterns are valuable. So you can use the logic-based piece to find your valuable pattern. And then just the implication is that there's a very valuable connection there. And that's what we're going to kind of keep working toward. And I'm going to pull up some of this work that I haven't done for about 10 or 12 years and start bringing that into the software component. So a key part of this, though, this whole aspect, is we need to have a basic, simple introduction component that we can start with to explain this and start motivating the ideas. And that's where the modification of Amar and Mariah's Frat Cube. They did a lot of work in teaching systems engineering. They did work in systems of in the high schools, secondary schools in the Seattle region many years ago of these concepts, and they tested them out. So I think that that's a really good place to start with that, and then but to use the cube itself and to establish a series of principles associated with the cubes, how they work, how information is encoded, and then that will help transition that to computer-based work when necessary. Okay, it's time for questions. All right, everyone's asleep.
I was actually waiting to hear what Jenna had to say because this is in her wheelhouse, I think.
Yeah, Michael and I have been down with flu for the last 2 weeks, so we're just barely functioning at this point.
Oh, sorry.
Oh, no.
Yeah, which actually means we're not going to be able to do what we expected to do in the mid-month session. We'll have to postpone that indefinitely. Don't know when we'll be able to get to it. But this is very interesting. I hadn't had a chance to look at it ahead of time. So if you want to proceed, Kevin, I'll see if I can come up with any further thoughts, but at this point I'm just following along.
And what was your motivation for starting this? You've been at this a long time. What was the early impetus?
Well, let's see. So Brian Marr was my professor at the University of Washington, and at that period of time, they they had a large industrial group that was bringing students in to have them, study this particular work. And I was working between the department that Brian was in, which was the civil engineering, environmental engineering. But Brian was a nuclear engineer, a nuclear chemist, something like that. And they had a very different type of environmental engineering up there. They had biologists, they had all kinds of people. It was a truly interdisciplinary systems thing, right? And so I bounced over to, and I was interested, anyway, I was interested in doing surveillance of environments, right? And one of those guys from Norway came in and he talked about how they surveilled their lakes and responded to all the acid rain coming from Poland from their power plants. And they were doing it with satellites, so I wanted to do it with satellite imagery. So I had that problem space I was working on. But then Brian introduced me to Warfield's work at that time, right? So all these laws, and wasn't necessarily the idea of how the technical part, right? The idea is, okay, once you have the technical information, how do you really get people to understand it? How do you make an attempt to get a positive response? How do you develop value systems? All of those things, right? So I went through a whole series of experiences with after the education process with large-scale government and other large corporate entities. And my upshot has been from all that is that the ability for people to communicate about their values and the people to communicate, being able to communicate effectively in detail is kind of missing. And it's missing for a number of reasons. And one of the reasons I think is addressed here, the fundamental piece, which is the overload, right? I don't know, I've said in numerous meetings where the executive would say, well, we just need to get smarter people, right? Because people can't handle this. And, finally, you just got to tell them, no, you got the smartest people you're going to get. You've got to be able to integrate these folks. And so there's just the concept that people have this limit, right? I look at long lists of things, right, that have no relationship to them. That, again, is kind of antithetical to relationships. And so the reason I'm doing this is because I've had a number of near successes in large-scale systems, right? In implementing something like this. And in every case where, I built up the computer-based system, we worked it up, we getting ready to deploy it, as soon as it became obvious to a certain level of management what its impact would be, the program went away. And so I said, okay, that's fine. That's clear. And so when I got the opportunity to actually go back to, and the time to look at this in more detail, then I started doing it. And it's, it makes a lot of sense to me anyway. Primary challenge, I think, is to figure out how to communicate, right? How would you communicate this way?
I like that phrase, the history of near successes. That's people usually talk about how we've had such terrible failures with this, that, and the other program, but having a lot of near successes is at least as evocative of what should be worked on.
Oh yeah, we had. I had one. Well, there was about 3 or 4 fellows at this one place, and we had a complete mission change. And we just had it. We had everything changed, right? And we had to redevelop everything, and no one really. Everybody just kind of in shock, and they were, doing their requirements, and they were doing their policies, and we were writing desk instructions, and there was just all kinds of activity going on, right? But it was all linear. It was all disjointed. No one really had a high-level model of what was going on. And so I was able to get some people, about 4, 2 in computing, and 1 in basically management, the guy that knew how the budget worked, and another guy that was able to do the graphics computing side. And we were able to put together a very good example of how these things could be integrated. But that we demonstrated that, and we're getting a lot of everyone recognized it would work, but then the mission changed again, and all of the funding went away. So time to go do something else. So it's interesting, but in my mind, I think from a basic aspect, this work is based on Mar and Marias. I think is the easiest way to go forward from a simple standpoint. So, but yeah, it's something I've always been curious about, Kevin. Do you think it has any value?
I was thinking back to in the 1980s when I was first getting interested in systems stuff, and I kept looking for diagrams or pictures that were like this, that were things that put order to the universe, and there seemed to be a lot, and some of them like Hall's stuff got referenced by many other people, so it just looked like a lot, but it was actually a lot of them were tracing back to a smaller set of theorists. But a lot of them wanted to use the geometric metaphor for ordering things, and many of those were associated, like the simpler ones. I mean, this one's kind of complicated because I think it's actually a hypercube, right? Because a cell within the top level can have a subcube that has 27 parts. So, but it's tough to draw hypercubes.
Oh well, no. Now this has 3 dimensions, and doesn't have 4 dimensions.
But you can have a cube of 27 pieces within a cube of the top level.
Well, the idea here, let's just take this one for example, right? So if I just wanted to say, okay, performance, metrics, and object, right? So if I say, well, what do I want my system to do, right? What do I want it to do? Um, if I just have performance metrics and objects with no subcategories in them, right? That's useful because that was the level of decomposition that Marr and Marias went into. They would say, okay, this is what I want my system to do. How well, the metrics, how well does it have to do it? So I match my performance with my metrics in each individual case, and then I select an object to do that, right? So you really don't need to drill down into it. The effectiveness metrics and the operational constraints and the design constraints, I added these three components to my experience of, yes, really not using the idea of requirements, because I think we need, for metrics, we need to have needs and constraints. And because requirements encapsulate both of those and they have completely different behaviors, right? But you can use this cube just using those three high-level concepts without breaking down. But if you choose to break down, you say, okay, then I'm going to have design constraints. That's fine. And I can just do that on one plane, or I can do it on another plane, or I can choose to do it, you know, on all three dimensions. So yeah, it's interesting. But it's the way I think that might be able to make the largest dissemination of the information anyway. So we'll see.
I think when I was kind of surveying the field, I was just paging through our library. For some strange reason, had the history of the Journal of, what was it, Journal of General Systems.
Oh yeah,
Science, that at one time Warfield was the editor when he was, and it was based out of Louisville, Kentucky. Like, what system science department is in Louisville, Kentucky? I don't know, but I wanted to go there. But yeah. So I was just paging through, you know, looking at diagrams, and it often seemed, you know, people would have the three, you know, they would, you know, if they had 3 dimensions, they use a cube. If they have 4, they use pillars, and they also have these linguistic metaphors like the 3-legged stool, or the 4 pillars of this, or the 5-pointed star. And that always seemed kind of platonic in the sense that it's searching for this idealized form that, you know, of course, you know, my way of breaking down the world has these 4 dimensions, which is why I use the pillar, or of course it has 5 dimensions, which is why I use a star or a pentagram, and that's why the universe is organized in terms of pentagrams or cubes. I'm always, whenever I see geometric metaphors, it's because when I was first looking at system stuff, I was looking across a lot of them and was like, okay, this one has 3, this one has 4, this one has 5, and why are they fragile? You know, what happens if it's not 3? You know, you can't use a cube anymore. Why is it happen that performance metrics and objects there's 3? Why isn't there a 4th thing? If you find there is a 4th thing, does it make the cube fall apart? I don't know.
Well, it overloads the human being, and so that's the reason for the 3. Of course, is the human limitation, the human constraint, and the idea of the jointly separable. The jointly separable is, yeah, these are jointly separable. You can use them individually, but they're much better if you use them together. And Combs did some work with some mathematics that basically fits into that realm, and we'll probably get to later on. But anyway, so that then you can actually do the calculation.
I think Warfield's argument for the 3 being based on the richest set that is comfortable is sort of, you know, that will stand the test of time. On the Peirce list, people argue about triadic relations and whether they're reducible to binary relations, and sort of in the abstract, apart from human capability. And there's no real basis for deciding one way or the other. I don't know, 4 elements, 3 elements, 2 elements, as you're saying. But in terms of the richest set that we're comfortable with, you know, it's really hard to argue with that, and that is, so that can be built upon with confidence. But I definitely appreciate what you're saying, Kevin. That people get caught up in symmetry and geometry, and you start to quickly feel like they are, you know, getting in too much navel gazing going on. They're in love with their design, you know, beyond the usefulness of it. Oh, and about the Kentucky, that was where James Miller, Living Systems Theory, ended up. So that's where ISSS was incorporated, and that's the Systems Association with Kentucky, Louisville.
Yeah.
All right. So, Kevin, are you going to have a presentation for March?
Yeah.
Okay.
So we can do. I can move on to what the second part of last time. We got into a discussion last time,
Okay.
before we went to the next part. So I'll make that link available through your. I'll send it to you, and you can send it out when you notify people. I think I did once before, the book about the playbook that was.
Okay, yeah, the playbook
Yeah.
thing? Okay,
Yeah.
good. Yeah, send that, and I'll send it out, and we'll
Right.
have that. And
And,
we'll continue on March 6th. We'll be going more into the current state of the software.
Joe, can you share the MAR material or point us to another resource?
Let's see. I will look and see what I can find.
Okay,
It's,
very good, thanks.
I have most of that I have in hard copy, but I will look and check out and see if I can find anything online. And if not, then I'll see about getting, if we can get copies out of something.
That'd be great.
Okay, great.
Thank you.
All right. Well, it was an excellent session today, and look forward to Kevin's presentation on the 16th. We continue on the playbook.
Okay. Bye-bye.
All right. Take care.
Thank
Have
you.
fun. Yeah.
Thank you.